In the previous lab session, you wrote some quick and dirty Verilog code to get an understanding of how the FPGA architecture works. In this screencast, we're going to be talking about Verilog as a language and what you can do with it. I'll be guiding you through some generic examples of Verilog syntax rules and the primitives available. Bear in mind that this isn't an oral reference manual. You can do a lot more with Verilog than I'll be talking about here, but this video will give you the essentials that you'll need to both cover the next few weeks' lab materials as well as to start experimenting for yourself. Before we get stuck into Verilog, I just want to briefly talk about hardware definition languages in general. As explored in Semester 1, we can use a hardware definition language to programmatically describe digital circuits. They allow us greater flexibility and finer level of control than designing via schematics and are far more verbose than netlists, so we can actually understand the circuit by looking at what's written. Hardware definition languages allow a designer to create the logic for a circuit, which can then be compiled by the development environment into a network of connections between primitives, which can be programmed onto a device. These languages are high level, so while you'll be doing a fair amount of lower level work, this wire connects to the input of this gate, etc., later on in the module we'll be starting to take a look at things like behavioural programming, where we abstract away from the actual circuit and describe what it needs to do as opposed to how it's laid out. There are two main hardware definition languages used in industry, VHDL and Verilog. The language that you used last semester, Jack, is also an HDL, but was designed specifically for the Nanto-Tetris course and doesn't have any real-world implementation. So we're just going to take a look at the differences between Verilog and VHDL. Similar to the differences between procedural programming languages, the two HDLs perform the same or similar functions, but have different sets of rules, syntaxes, and structures. In this example, I've described a simple 4-bit multiplexer in both Verilog and VHDL, so you can get an idea of the differences between the two languages. You can see that VHDL is a bit more verbose than Verilog, so you're writing more code, but it's easier to read. Verilog, on the other hand, looks a lot more like C code, so you should be able to get an idea of what's going on based on your knowledge from embedded systems. There are also some small variations, such as Verilog is case-sensitive, whereas VHDL isn't, and Verilog allows you to change the data type of a variable at runtime, whereas in VHDL everything is fixed. There really isn't that much of a difference in terms of the two languages' applications. Verilog is a bit better for low-level modelling, but not significantly. It often just comes down to the designer's, or rather the design company's, choice as to which language is used. Both are widespread across the worldwide digital design industry, and once you know one well, it isn't too hard to switch to the other. Unlike in procedural languages, a single compiler can deal with both Verilog and VHDL, as they both compile down to netlists anyway, so projects can be a mix of both languages, although this isn't generally advised for readability's sake. So for the rest of this screencast, I'm going to talk about Verilog syntax and give some implementation examples along the way. As I said earlier, this isn't going to be a full reference, as that would be hours upon hours of tedious lines of code. If you ever need the Verilog reference manual, it's freely available online. Just to set everything into context, let's take a look at this example Verilog file. A module in Verilog is the same as a chip in Jack. It's a block of code with a specific purpose, usually defining a specific function. As I mentioned in the previous lab session, we use a separate Verilog file for each module, with the file name matching the module name. Verilog files start with a descriptive comment, giving the name of the design, the creator, and the date, as well as a short description of what it does. Why do we include so much information as standard? Well, for one, it's just good design practice for your own reference. But as we'll be talking about further down the line, a lot of FPGA development relies on the reuse of modules, and therefore it's important to include a healthy amount of detail. One thing that's very important when it comes to FPGA development, and something that you're going to have to work hard to remember, particularly when we do sequential logic later in the semester, all HDL is executed in parallel. You're describing a circuit here, not a step-by-step list of instructions. It can be very easy to forget this when you're writing behavioural code further down the line, and that can result in significant errors in your circuit. So let's take a more in-depth look at how modules are constructed. Modules are the basic unit of hierarchy in Verilog. They're self-contained blocks of code not too dissimilar from functions in C or C++. You can think of a module as a standalone integrated circuit designed for a specific purpose. This is probably why the equivalent structure is known as a chip in Jack. Modules are contained within these module and end module statements. I write these in straight away when I create a new module, otherwise I inevitably forget the end module statement and then wonder why nothing works when I compile. The module name is an identifier for that particular module and must be unique within the project. This doesn't mean we can only use one instance of the module within the design. I'll be talking about module instances in the next screencast, but it does mean that you can't have two modules named the same thing. As I've mentioned previously, the module name should match the Verilog file name, and we declare only one module per file. Following the module's name is its interface, in which we declare the module's ports. The interface for a Verilog module can be thought of as a pin map for an IC, where we detail what the pins are and add a descriptive comment to say what they do. All of the module's inputs and outputs and their respective widths must be declared in the interface. You can't just add them in throughout the module. For readability's sake, we declare each port on a different line, with commas between all port declarations. The interface is then closed off and terminated with a semicolon. There are three different ports that can be used: input, output, and bidirectional, declared by the input, output, and in-out keywords, respectively. So for the next week or so, we'll be concentrating on low-level implementation of combinational logic circuits. So we'll be making good use of Verilog's gate-level primitives. Verilog has a fairly large number of logic gates explicitly defined within its language. You can use AND, NAND, OR, XOR, NOR, and XNOR gates right out of the box. We can also use both inverting and non-inverting buffers in order to negate or stabilize signals using NOT and buff, respectively. A handy feature of gate-level primitives in Verilog are their built-in ability to be as wide as necessary, so we don't have to redefine a gate for every width we require. For multiple input gates, we define them by using the gates keyword, followed by an open bracket, and then we state the output connection, followed by n input connections, depending on the width required, before closing the bracket. For example, we want to declare an AND gate with two inputs A and B, connected to a wire called A and B. In Verilog, we'd write AND, open bracket, A and B, which is our output wire, comma, A, comma, B, close bracket. If we wanted more inputs, we just continue to add them within the brackets, as you can see with this 4-input XOR gate. With our buffers, they only ever take a single input but can have multiple outputs, so we define them again with the gates keyword, but the first n terms will be taken as outputs and the final term being our single input. For example, a simple 1-to-1 NOT gate can be described simply as NOT, open bracket, our output NOT A, and our input A. A 4-output buffer, however, is described by buff, open bracket, our 4 outputs, W1, W2, W3, and W4, followed by our single input B. You may have seen me in the last lab session make use of wires to string multiple gates together. Wires are one of the two main data types which can be used to represent variables in Verilog, along with registers. Wires are used in combinational logic to link together parts of the circuit, whereas registers are used to store values. There are some specific rules as to what wires and registers can and can't be used to do, but we'll cover this in detail later on in the semester. Wires and registers can be exclusively internal or can be made externally available for connection outside of the module. Wires are declared as shown here, with internal wires using the keyword wire and input and output wires taking those terms as their respective declarations. We can declare wires as an individual net or as a bus by declaring a width alongside the type. Wires are given unique names so that they can be referenced inside the module, in the same way that you'd give a variable a name in C. As a general rule, we declare the data type, followed by the width in square brackets, and then the wire's name. The width is denoted by the range of bits it covers in the format most significant bit, least significant bit. When we refer to the individual bits of a bus in the implementation, we address the width and the name in reverse, in a similar way to accessing an array in C. Now that you've spent at least 18 months working with programming languages, it's time to become a bit more professional with how you write your code. While in the past it's been okay to name variables whatever you like, within reason, we're now well on our way to becoming proper engineers, so we're going to start to focus on good practice in our variable names. Now in Verilog there are a couple of explicit rules which need to be followed when naming your identifiers. All identifiers should be a sequence of letters, digits and underscores. As with most of the programming languages, we can't use spaces or symbols, but you should know that by now. In Verilog, the first character of an identifier can only be a letter or an underscore, so we can't start with a number. So taking a look at the examples here, the top two are valid, as they start with a letter and don't contain any spaces, whereas the bottom two are invalid due to the space and starting with a number. Along with the explicit rules, there are also some good practices which you're expected to follow. Module names should start with a capital letter and use camel case, so each word in the name is capitalized. Variable, instance and port names should start with lowercase and use camel case. Parameters and constants are all in capitals, with words separated by an underscore. And finally, when dealing with inverted signals, their identifiers should end in _n, so it can be easily spotted when viewing your design. So again, we have some examples here of good and bad practice. While these names are all valid as identifiers and will compile, they don't make for professional code. In multiple modules this year and going ahead, you're going to be assessed on your code quality, so you need to get into good habits sooner rather than later. So we're going to talk now about how signal states can be represented in Verilog. The first two are easy to assume. Logic high and logic low are represented by a 1 and 0 respectively, but we also have these other two states, high impedance or unconnected and unknown. The first of these makes sense when you take into account that we're working with physical hardware here. We can completely disconnect a wire. This doesn't result in a logic low by default, as we could have logic levels which aren't 3.3 and 0 volts, and plus, it isn't a logic low, it's gone altogether. This can be represented in Verilog by the letter Z. The unknown value is another tricky one, in that it doesn't have a physical representation. There isn't an unknown state that a wire can be in, only high, low, or unconnected. We use unknown as a placeholder for when we don't know what state the wire is in. You'll see it in the next lab session when we start doing simulation, where until an output signal is actively driven, its state will be denoted by an X. Numbers in Verilog can be specified in various radixes, namely binary, octal, decimal and hexadecimal. However, this is only for display purposes. Again, we're dealing with physical wires and registers here, so they will always be stored on the device in binary. When declaring numbers, we follow the format of size, followed by an apostrophe, then the flag for radix and the actual value. So for $B1001 will store the binary value 1001. If the width is larger than the number being stored, the result will be 0 padded. Be careful to remember when specifying the size that you're specifying it in terms of number of wires required to hold that binary value. So even if you were to specify a single hex value, for example, you would still need a width of at least 4 to hold all possible values. If the sizes don't match, and you try and store numbers larger than can be held in that width, your design will still compile, but only the least significant bits of that number will be stored. For high impedance and unknown signals, you can autofill a width with just a single placeholder. Bear in mind this doesn't work for 1s and 0s or any other number, just for high impedance and unknown. So that pretty much covers the basics of what you'll need in terms of Verilog for the next few weeks. Once we start abstracting away from low-level implementation, we'll talk again about things like operators and arithmetics and other things concerning behavioral Verilog. But for now, we'll stick with the primitives and let you start building more complex designs. In the meantime, if you're uncertain of anything regarding Verilog, I highly recommend you take a look at ASIC World. It breaks down the reference libraries into a nice, easy-to-read format and contains a lot of examples of how things are implemented. If you're ever getting any weird syntax errors or simply can't remember how something needs to be written, make it your first port of call for finding out the answer. Be aware, however, that you won't have access to it during the test, so don't rely on it too much.